In this problem, we take a look at problem 3.4 that considers a hypothesis test involving two different averages. Let's first kind of classify this. This is a hypothesis testing problem. We're trying to determine if machine 2 is faster than machine 1. It involves an average, specifically two different averages. And so this is a two-sample problem. It is a one-sided hypothesis test. Because the question is machine 2 faster than machine 1? This involves a large sample. And so therefore this involves the test statistic Z. The null hypothesis will be that the two means are indeed the same, and that the difference that's observed in these two samples is simply attributable to chance. The alternative hypothesis is that the second machine does a better job than the first machine, and therefore mu1 minus mu2 is less than 0. Okay, so now to compute the test statistic, first off we need the standard error. That'll be equal to the square root of the first standard deviation squared divided by 60 plus the second standard deviation squared divided by 60, and that is equal to 0.85489. From this we can get the test statistic Z. That'll be equal to the observed difference of 73.8 minus 76.1 minus the expected difference of 0 divided by the standard error for the difference, which we just computed. And that is equal to negative 2.6904. Okay, from this point, there are two possible ways of proceeding. First way of proceeding is by finding the test statistic, the critical value, pardon me. The value of alpha by default is equal to 0.05. This is a left-tail test given the form of the alternative hypothesis. And then we find that the value of the test statistic is negative 1.6449. The value of the critical value is negative 1.6449. The test statistic falls in the rejection region, and so therefore our decision would be to reject the null hypothesis. The second way of proceeding is to find the p-value, meaning we find the probability of an event this extreme or more extreme, negative 2.6904. And we find the area to the left, and it turns out the area to the left using the normal CDF command or else norm sdist on a TI calculator, we get 0.0063, there's 0.0036, pardon me, and that is less than the given value of alpha. And so therefore our decision will be, let's type that down here, our decision is that we reject the null hypothesis. Either way, it appears that machine 2 is faster than machine 1, being able to fill more cans per minute. Okay, before turning to the remaining parts of this problem, let me copy over the most important pieces of information that we'll need for the future. The first thing that we'll need is the value of Z alpha. And so we'll just put that over here, that Z alpha is equal to Z alpha is equal to positive 1.6449. Remember that the Z alpha is always a positive number as long as alpha is less than a half as usual. The other thing that we'll need is the value of the standard error. And so let me mark that over here, that the standard error is equal to 0.85489. The second part of the problem involves the power of the test if machine 2 is indeed faster than machine 1 and can fill on average 3 cans per minute more than machine 1. To do this, we will use the formula that we presented in class, that beta, the probability of a type 2 error, is 1 minus capital Phi times negative z sub alpha minus delta prime minus delta 0 over the standard error. And I'll just rewrite that as sigma 1 squared over n plus sigma 2 squared over n. So in our case, this is equal to 1 minus capital Phi of negative 1.6449. So the z alpha is positive, so negative z sub alpha is the same critical value that we had before, minus delta prime is the new difference under the alternative hypothesis, which is negative 3, minus the hypothesized difference under the null, which was 0, divided by the standard error, which we found out already was 0.85489. So this is equal to 1 minus phi of, and then just doing the arithmetic, we get this is 1.8643. And so remember that the phi function is the area to the left under the normal curve. So 1.86 would be over here. So the phi function gives the area to the left, and so 1 minus phi would be the area to the right. And so using the normal CDF command, or else norm sdist, we find that this area is equal to 0.0311. That is the value of beta. The question asks for the power of the test, and so the power of the test is equal to 1 minus beta, which works out to be 0.9689. And so there is the power of the test if machine 2 is indeed capable of filling 3 cans per minute more than machine 1. For the third part of the problem, suppose that we want beta of 3 to be not equal to 0.03 but equal to 0.001. What is the number of cans that must be filled by both machines to make that happen? So the formula for this would go that we want the sigma 1 squared over n plus sigma 2 squared over n. So we're assuming that the same value of n is used for both machines, is equal to delta prime minus delta sub 0 squared over z sub alpha plus z sub beta. Now z sub alpha we've already figured out. The area that has the 95th percentile under the bell curve is 1.6449. To get the value of z sub beta, we do the same thing, except this time I want the area to the right to be equal to not 0.05, but further out, so that the area is 0.001. So this is the 99.9th percentile of the normal distribution, and we find that to be equal to 3.0902. So setting up the problem, we have 5.2 squared divided by n plus 4.1 squared divided by n is equal to delta prime is negative 3. Negative 3 because, again, the second machine is faster, and so mu1 minus mu2 would be negative, minus 0 squared, all divided by 1.6449 plus 3.0902 squared. So this now becomes an algebra problem solving for n. And so just doing the algebra solving for n, the first steps here would probably be just simply squaring these out and then combining the fractions because we have a common denominator. So doing the work, we get that n is equal to 109.24, and we round up to be safe, so we'll take n to be equal to 110. And so there is our answer for the number of that must be done for both machines. Not surprisingly, we need a bigger sample in order to reduce the value of beta. Finally, for the last part of this problem, suppose that machine 1 should be tested twice as much as machine 2, then determine the number of tests that must be done. So the formula is going to look an awful lot like the one that we just did, so let me just simply copy that and use that as my starting point. Except this time, the number of times that this first machine must be tested must be twice as large as the amount for the second machine. So I have a very similar looking formula, except I have different denominators. Now once again, this becomes basically an algebra problem to solve for n. Again, we probably would get a common denominator here and solve for n. So doing the work, we get that in this case, n would be equal to 75.56, which will round up to 76. And so the second machine must be tested 76 times. And so that means that the first machine must be tested twice as many times for 152. And so that would be the number of times that the machines would have to be tested if the first machine is tested twice as often as the second.